Okay, so the second law, there's lots of ways to say the second law. So the second law gets hard to understand. Okay, systems tend toward a net increase in entropy or disorder. Okay, another way to say it is a heat flows from hot to cold. Now these are the same thing. Okay, let me explain why. Let's imagine that you've got hot stuff and you've got cold stuff. These could be two pieces of metal or fluid or something like that, right? In this case, I've got more order. I know where the hot stuff is. I know where the cold stuff is, right? Once the heat flows from hot to cold, we've got lukewarm stuff, right? It's all just lukewarm. I lose the information, the orderliness of the hot being here and the cold being there, okay? Now, when you do the calculation, you'll see that when heat flows from hot to cold, that the calculation actually shows that entropy increases, okay? But I will, save that for another video. Okay. Another way of saying the second law is that no device can turn all of a given amount of heat to work. And this is the same thing, right? Because heat, remember, is just chaos. A hot gas is molecules moving in all random directions. Work is literally like we lift a book from here to here. That's incredibly orderly. That is, it's very compact, right? Or it's maybe a baseball. We speed up a baseball. We could speed a baseball up to 90 miles per hour from the heat. Well, the heat is disorderly. The baseball is very orderly. It's one single particle moving in a straight line. All the particles are moving exactly in the same direction. Okay? So that's why this is the same as the first one. Okay? Let's see. Systems tend to move toward more probable states. All mixed up is more probable, that right? If you drop a box of dominoes, it's more likely that they'll fall in a disorderly way than they will fall in consecutive order. Okay, it's much less likely, right? So you could, I've got demonstrations of this, right? If the most probable state for a bunch of coins, right, is that half of them are heads up, half of them are heads down, right? But if you shake them long enough, right, and you start with all heads up, eventually you're going to head toward a more probable state, which is 50-50, or roughly so, right? I was demonstrating that to some students one time, and I had like 4 pennies in there, or more than that maybe, and I shook them, and I looked down, and, to my amazement, they all came up heads up, and I'm right when I'm saying that's very unlikely that it will be heads up, right? I've got a heat flow simulation. I'll show you that on the computer. I'm not going to show you that here. Mixing of warm and cold water, we talked about that, right? Heat engines, right? Heat engines will tend to waste heat, right? Because you've got the QH, right? You've got some amount turning into work, and then you've got wasted heat, right? So they tend to, one way to say this, the second law is, the first law is you can't get something for nothing. The second law is you can't even break even. Right? Because since there's no way to turn a given amount of heat into work, you're always losing some. You're always losing this low temperature heat, the QC or whatever you want to call it, right? And then, you can look at entropy in very simple terms, right? If I drop a plate from the table, it's going to smash. The pieces will fly across the floor. This doesn't violate the first law, but it does violate the second law. If you saw a video of all the pieces flying toward each other on the ground, their velocity causing the plate to reform molecular bonds, right? And then create the plate in such a distorted fashion that it leaps back up onto the table, you would know you're seeing that backwards. Or a cigarette reverse burning, right? So we would say, a lot of people say that entropy is time's arrow. That is, if you see a video and you see it backwards, you can see processes where the disorder is decreasing randomly, right? And the notable example was my father was teaching a class on, I think, French film or something like that, He was taught Shakespeare, but during the interim, during Jan term or whatever we called it, interim, he would teach a course on French film, and they showed this. There's a woman's hand flung out of the bed, and she's got a cigarette in her hand, and it's a voiceover. Okay, there's like people talking in the background, right? And you see the cigarette burning, and some student sitting in the front row notices that the smoke is actually going into the cigarette, and as the conversation goes on, the cigarette gets longer and longer. Well, this can't happen, right? We understand burning is a very entropic process. It increases the entropy in things, right? So you can tell that what had happened to that clip was that it had been fed in backwards. They dropped it, they fed it in backwards. Since it didn't have a soundtrack on it, since it was a voiceover, they couldn't tell which way it went, so they 50-50 chance, and they got it wrong. And the thing that's interesting is that you wouldn't see it on a normal projection screen, but at McAllister they had a rear projection screen, so you could sit right up against it and see this old actual projection film, and you could see it really close, and that's the only way you could see it. Wow, I'm just really talking a lot about the second law. Second law is cool. Anyway.